Okay, all right. Well, hello, and happy week 10. Happy Monday. Last week of, I guess, lecture. Some of you, I guess you'll have your finals this week, but our final is next week, and I think one of my finals, I forget which one, is like a Friday final. It's always the dreaded Friday final, dreaded for professors as well. But we're just at the mercy of the registrar's office. So so that's what we got going on. But I'll cover today. We'll look at just miscellaneous topics. Wednesday, I'll talk about what you can expect on the final exam, and then I think I'll just cancel Friday's class. So we'll just so last bit of new stuff here. Wednesday we'll have I'll talk about what you can expect for the final, and then Friday you can enjoy off. Okay. I guess that's not really off because you have to like studying and stuff for your other classes, but you won't have to. I won't be adding to that pile, I guess, as far as new stuff goes. But okay. Oh, and I do have a favor to ask of you, and that is to fill out your course evaluations. I think this link takes you to filling out the course evaluations. I don't know. You can try it out. But yes, that does. I know sometimes students wonder, like, do these course evaluations count for anything? They do for me, in that I am a lecturer. So I don't know if you guys know this, but at UCLA there's a few different types of faculty members. So you have tenure track faculty members. These are the research professors who their promotions are primarily based on their research. So what published papers they're publishing, what grants they've been awarded, things like that. They bring in a lot of kind of money, and they're really responsible for the advancement of science. In that, like, anytime there's a discovery or a breakthrough, it's going to be a research professor who's responsible for that, their labs and stuff like that. So they have that. You also have kind of adjunct faculty who either are looking to get a tenure track position somewhere, or maybe have a separate career somewhere else. And then you have full-time lecturers, or like myself, whose primary job is teaching and only teaching. I don't do any research, so I'm strictly evaluated on my kind of course evaluations and things like that. So those do make a difference as far as, your, like, our merit reviews and things like that. When it comes to tenure track professors, I'd say the course evaluations are weighted much less importantly versus their research contributions. So there are sometimes students go, oh, why is this person still here? They're not a great teacher and things like that. Probably the answer is going to be because they're making very significant contributions to just the fields of science through their research, and it is like different giftings, being able to conduct research versus being able to just present and teach material to undergrads. So we love it if there's overlap and the person is skilled in both, but I am, I think, skilled on the teaching side, but I'm not very skilled on the research side, and some people kind of have the opposite set of giftings there. So anyway, all to say, your course evaluations do matter, and so I greatly appreciate you taking the time to fill those out. All right, let's just take a look. Want to look at a couple, I guess, miscellaneous topics. One of them being this function optim. Okay, so let me do that. So we looked at numeric optimization a few weeks ago, and then we then looked at randomization tests and bootstrap and things like that. But now I want to kind of go back to numeric optimization. And this is strictly kind of like, how would you actually go about doing numeric optimization on the computer. And I'd say a lot of times you will just use this function that exists, okay? So it's a little bit funny, but in some of these courses we teach you these algorithms and these things and how they work, but then when you actually do it, you're just gonna use the prepackaged things, right? It's kind of like, I don't know, you go to a wilderness course and they teach you how to like make fire with sticks, but when it comes down to like making fire, you're just going to use a match or a lighter most of the time, okay? But I think there's a merit in learning kind of these, like how it works underneath and stuff like that, right? So anyway, when it comes to just actually optimizing a function in your day-to-day, you'll probably just use Optim. Optim is kind of this general purpose optimization function in that it's going to work pretty well in most cases, but certainly in certain applications, there might be a specialized optimization function that's really designed for that particular application. So for example, neural networks, our popular machine learning and popular tools and kind of AI and stuff like that, you could use Optim to try to optimize a neural network to try to train it and get the appropriate parameters. And it will probably work for neural networks up to a certain size, but beyond that, it'll probably struggle. And so, for an open area of research in AI and whatnot is, working on kind of more specialized optimization algorithms that are able to kind of train these massive neural networks, or I guess they're called, for ChatGPT, it's like large language models. And when they say large, they really mean large because it's like hundreds of millions or billions of kind of parameters to estimate in these things. And your general purpose optimization tool probably not going to work the best. Okay, so sometimes you do need a specialized thing, but I would say for a lot of cases this is going to be work pretty well. This is the argument. If you look up kind of the help for Optim, this is what it says. And so you see the arguments going in. You've got par, you've got fn, you've got gr, you have the method, lower, upper, control, Hessian, stuff like that. So let's just talk about some of these things. Par is going to be a vector of initial parameter values to be optimized over. So the idea here is you've got some kind of function that you want to minimize. So Optim is a minimization function, optimization that searches for minimum. If you want to maximize it, you just multiply your function by -1, okay? And that will maximize it. But basically, this function, is it takes arguments, variables coming in, and it produces one output value. So we can only optimize something where it produces just one value on the output. If the function produces more than one, we're not going to be able to optimize because they might work in different directions, right? Like, and one value might go up and the other one goes down, and which one are we going to prefer? So the function can only produce one value, and we want it to go down. Okay. So what did I write? The function's first argument needs to be a vector of parameters over which the minimization takes place, and then the function must return a single scalar value. GR allows you to provide a function that will return the gradient. The gradient is kind of like a derivative, but multivariate, and it's kind of like so I think in homework 5 we had you do Newton-Raphson method, and in Newton-Raphson method you wrote a function that returned two values. One was the value of the function itself, and then the other value was the function of the derivative, and you used both of those values to try to figure out where your next iteration location would be. here in Optim, basically you would separate those two values out. You'd have one function where you plug it in and gives you the value of the function itself, that's going to be fn, and you'd have a separate function where you plug in the value and it gives you the derivative or the gradient there. Okay, so you have two separate functions, but basically you're going to use those two values to try to figure out where your next iteration is. If you don't have the gradient function, okay, and you want to do gradient-based stuff, Optim can figure this out. It will do a finite difference approximation. So one of my earlier lectures, we said, you know, if you don't want to figure out the gradients, you can just kind of add a 0.001 or whatever and see how much of a difference that makes, and estimate your gradient or estimate your derivative that way. And Optim also uses a similar technique, okay, to do something like that. There's additional arguments. You can specify what method of optimization you want to use, and so one of the default methods is Nelder-Mead, which we talked about. There's a whole bunch of other methods. A very popular one is BFGS, which we did not cover in this class. It is a gradient-based optimization method. I cover gradient-based optimization in 102B, so that's the next class in our computational series. And I think most of the other classes also cover gradient-based optimization somewhere along in 102B. I don't cover this specific algorithm. I just covered general gradient descent. And BFGS is basically a modification of gradient descent with taking into account, I guess, curvature information. BFGS stands for these four people, Broyden, Fletcher, Goldfarb, Shano. That often happens. People want to make sure their name gets credit in the algorithm, and so you'll see things with a whole bunch of letters in them, and so anyway, that is the method there. Okay. Okay, let's try this out. This is how do you use Optim? Well, first you have to write a function that Optim can work with. So let's say we wanted to minimize this particular function, x squared minus 2x minus 0.5xy plus 2.5y squared, and I put that into Wolfram alpha, x squared minus 2x minus 0.5xy plus 2.5y squared. And you know, it's this paraboloid. I think this was the exact same function we used for the coordinate descent, and it's kind of this, you know, big paraboloid bowl, and you just want to kind of get to the bottom of the bowl to find the minimum. All right, so anyway, this is, if I said write this function in R, I imagine you'd probably write it something like this. Okay, you'd say here, you know, it's a function of x and y, and then you plug in those x and y values, and this is the only line in the function, so this is the value that the function will return. Okay, and so if you plug in 0 and 0, you'd get, you know, you plug in 0 squared minus 2 times 0 minus 0, you know, you get 0. Okay, you plug in, you know, 1 and 2 or whatever, you get different values. This function, however, if you give it to Optim, it will not work, right? And so this is, you know, when students try to use Optim and they try to write a function that works with Optim, they often get frustrated because if you're not familiar with how Optim works, you know, something like this fails, okay? And the reason why it fails is because Optim allows functions that only take in one argument par, okay? Now par can be a vector of multiple values, but it has to be all grouped together into one argument. And so so to convert this into a function that does work with Optim is very simple. Basically, you just put x and y together into a single vector called par, and then in the first couple lines of your function will be to kind of unpack par into the different components. So I'm going to just say, okay, par is going to be a vector of two values, and we're going to say par square bracket 1 is going to be x, and par square bracket 2 is going to be y. And then now that I have an x and y, I can calculate this, and that will be now the function will work. with Optim, okay? When you read other people's code, if they're using Optim, you might see them, I guess, save a few lines of code by just kind of combining everything into one line. And you'll see par square bracket 1 squared minus 2 times par square bracket 1 minus 0.5 times par square bracket 1 times par square bracket 2 plus 2.5 par square bracket 2 quantity squared or something like that. So you might see something like that. And again, that would also work where they've basically done the unpacking of par into its components x and y just all within one line here. But I think for me, my personal preference is to use letters like x and y and to unpack it kind of like this. Par 1 and par 2 is x. Par 1 is x and par 2 is y, or something like that. Okay, and so now that I have this function g, I can use Optim to optimize it. All right, and so this is how it works. We call Optim. We say par equals, and then you give it just some arbitrary starting values, and then you say the function I want to optimize is g. Okay, and so we can see from Wolfram Alpha, the optimal global minimum takes place at 4,39, 40 over 39, and 4,39. That's the coordinates x and y, and then the value evaluated at the minimum is negative 40 over 39. So that is what Wolfram Alpha states, and indeed we can see what we get. And so 40 divided by 39 is 1.025641. 4 divided by 39 is 0.1025641. And when we asked R to calculate this, default method being Nelder-Mead, it says, okay, I got negative 1.025641 as my value at the minimum, and its coordinates are 1.0255 and 0.10247. So kind of close, pretty close to the actual values of 1.0256 and 0.10256 not perfectly such, but it gets there. It says it took me around 85 iterations to get down there. Convergence 0. 0 is basically a status, and 0 is what you want. 0 means I did converge, and its convergence criteria is basically like I'm not really, my value isn't going down, right? So once it reaches kind of like the minimum here, and it doesn't see anything that it can get into to anything lower, it just says, all right, I think we've reached the minimum here, okay? And so this is what we get. So this is the minimized value, which indeed is equivalent to negative 40 over 39, and that is indeed the answer that Wolfram Alpha also states. It says, yeah, your minimum value is at negative 40 over 39, and that's kind of what we get, and then the locations are here and here. You can, for fairly smooth, simpler convex functions, the BFGS method probably gives you better performance. And so here I'm going to call the same thing, Optim par negative 1, 1.5, function is g, and I'm going to say method is BFGS, okay? And here we get like really like almost the true values exactly, right? 1.025641 and then 0.1025641. So we feel like, oh, this performed a lot better or something. The optimized value, negative 0.1025641. So in both of these cases, we got the value like spot on, okay? Here it took 17 iterations, gradient 5, I don't know. Also reached convergence here, okay? And so when you look at this, it feels like, oh, this did like a lot better than this. I don't know if I would agree. I mean, yes, from a strict standpoint, like these numbers are a little bit off and these ones are like almost exactly on. But basically, if you look at the value itself, the value of the minimized function, that's pretty much the same. And basically what's happening is, imagine this thing kind of, it's this paraboloid, right? It's this bowl. And at the bottom of the bowl, like really close to being flat. Okay, the bottom, there is like a true bottom. Okay, there is a minimum, but it's really like almost flat near the bottom. Okay, and so for this one we're finding like the true minimum right here. Okay, and the other one is just like off by a little bit. Okay, and so if you look at it, from the side, is there a real difference from like this location and this location? Probably not really. Okay, and so when you look at the value, you're getting pretty much the same value here for the value, but as far as what are the coordinates of that minimum location, it's a little bit off. Okay, but if you were looking for exact values, you wouldn't have used a numeric optimization method to begin with, right? So numeric optimization, you are accepting the fact that everything is going to be an approximation. Okay, if you need exact numbers, then you have to kind of do the analytic approach. But yeah, numeric optimization will give you pretty good estimates a lot of the times. Okay, but again, we have a whole bunch of these different methods because some of these methods will fail, right? Like you saw in homework 5 when you did Newton-Raphson and things like that. Some of those problems were intentionally, not converging, or intentionally like showing you some of the problems that could arise with these things, just so you don't get the wrong impression that these things work all the time. Okay. Let me give you your first view quiz answer. The letter A. A as an apple. A as an apple. Here's another example. We can approach linear regression as an optimization problem. So you guys are taking 101A and things like that. And we can say, hey, let's try to minimize the, when you do linear regression, what you're trying to minimize is the sum of squared residuals. What's the difference between what the actual value is and the predicted value, okay? And what you're predicting is basically the intercept plus slope times your x value. And so we want to say, okay, how do we pick the intercept? How do we pick the slope so that the difference between the line we're predicting and the actual values is as minimized as possible? Now, this is already a solved problem. We know exactly how to get our slope and how to get our intercept that will optimize and give us the smallest sum of squared residuals. But here I want to kind of show it working as an example with Optim. Okay, so let me do this. I'm going to just create my set of points, 1, 2, 3, and 4 for x. Y is going to be the points 2, 6, 4, and 8. Okay, and I'm going to plot x and y. I'm going to set my x limits to be 0 and 5. My y limits to be 0 and 10. Y character 19, solid dots. Okay, so these are the dots here, all right? And I can say, the best fit line, okay? I'm going to create the model that I want. I'm going to just do y predicted by x. That will be my model. And I can plot the fitted line as a red line here, okay? So we can do that. All right, how do I turn this into an optimization problem? Okay, I might want to say like, hey, what is my sum of squares residuals, right? So what if I create this plot and I said AB line okay, what if I drew this line, okay, where my intercept is 0 and my slope is 2. So it goes through these points here. What is my sum of squared residuals here? Okay, well, the sum of squared residuals, I have no residual here, I have no residual here, but for this point at 2, 6, my line would predict 4. So I get a difference of 6 minus 4, I get a difference of 2 squared. And over here my line is predicting 6, my actual value is 4, so I get a difference of 2, I would get 2 squared. I would get a sum of squares of 8, right? 2 squared plus 2 squared, I get 8. So basically I want to be able to find a way to calculate these sum of squared residuals. How can I do that? Okay, so we'll create a function called SS for the sum of squares. And what we want, in order for it to work with Optim, it needs to come in as par, okay? And there are two things. We want to figure out the best intercept and the best slope. So I'm going to unpack par into intercept. So I'll just say par 1 is going to be my intercept, and my slope is going to be par 2, okay? And let me take my data. I'm going to put my data into the function. Okay, so we got x and we got y. And what we need is we need to make our predictions. Okay, so our predictions are, maybe I'll call this y hats. Okay, my y hat will be my intercept plus my slope times x. All right, so this is how I'm going to make my predictions. And then my residuals will be the difference between y minus y hat, actual minus predicted. Okay, and then the value that gets returned is going to be the sum of the residuals squared. I think that should be right. So this is the value that is returned, and that's basically sum of squares residuals. All right, so if I did sum of squares, if I have 0, 2, indeed I get 8 as my sum of squared residuals if I plug in this thing. And if I have a different line, if I say 2.5, 0 here, oh no, not 2. I would want to do 5. Okay, I can say, hey, what are my sum of squares here? Sum of squares on 5, 0, right? And we get 20, right? Because I get 1 squared, and 8 minus 5. This is 3 squared is 9. So 9 plus 1 plus 1 plus 9 gives me 20, indeed. All right. So we want to be able to try to evaluate this. And so to optimize this, we're going to call Optim. Just give it some arbitrary starting value. So maybe I'll do 0, 0. Okay. And then the function I want to optimize is my sum of squares function. Okay. And I could say, all right, give me what values optimize this. And it says intercept 1, slope, or intercept 0.99965, slope of 1.60, and the optimized value is 7.20001. I might get better values if I use BFGS. So I could say method equals BFGS, and you can try to play around with this. All right. And so indeed I do get the exact values of 1.0 and 1.6. And I can compare that to my model that I fit with LM. The model I fit with the LM said the intercept is 1 and the slope is 1.6. And so using our optimization function, we're getting the same kinds of values here. Again, it's a little bit silly because this is a solved problem, but it is I think it's kind of neat that we can treat it as an optimization problem. So again, here's the function. I guess I called it B0 and B1 rather than slope and intercept and slope, but same kind of idea here. I got this is y hat, calculate our residuals, and what we want to do is minimize our sum of squared residuals. Okay, and so using that, we get parameters 1.0 and 1.6. Okay. I guess I'll give you your second view quiz answer, which is the letter E. E as in elephant. E as in elephant. Okay. I wanted to show you a little bit about kernel density estimation. This is completely unrelated to everything else as well, but it is a thing that pops up and is used frequently, and I wanted to just illustrate a little bit how it works, okay? I think we all understand histograms. We've created histograms ourselves, and if I gave you a small data set, maybe like 60 values or 50 values, and I said make a histogram yourself, you might grumble, but you could do it, okay? You would have to kind of, if I sorted them for you, it'd certainly make your life a lot easier, right? And if I said, hey, make a histogram with this, and if the data values come in all sorted, you can say, all right, I'm going to create some bins, I'm going to tally up how many fit in a certain bin, I'm going to draw a bar with this height, and you could create a histogram. And so here I've generated 60 values from the normal distribution, and I said make a histogram. Okay. Most of the time, our histogram, the height of the bar is the frequency. You just count how many values you have, and the height is equal to how many values you have there, right? So if you have one observation, you'd have a height of 1. You can create something called a relative frequency, where you take the frequency and you divide by how many observations you have. Okay, so if you have 60 observations and you have 3 observations within a certain bar. Okay, so let me just kind of show you. So I'm going to do set seed 20, and I'm going to do my sample is R norm 60, and then I'm going to go ahead and sort my sample, and I'm going to just round it off to say 3 places here. So we can see this, and I'm going to create a histogram of my sample. So if I do a histogram of my sample, I get 1 observation, 3 observations, and I can ask for a relative frequency histogram. And for relative frequency histogram, what I would do is I would say, okay, there's 3 observations here in this one between -1.5 and -2. I have 3 observations, these 3 observations. And so my relative frequency would be 3 divided by 60. It would have a height of 0.05, 3 divided by 60, and we would do that. And if you create a relative frequency histogram, the feature is if you add up all of the heights would all add up to 1, right? So, so I'll just write this: relative frequency is equal to the frequency divided by total count, and then the sum of all heights, bar heights, or sum of all bar heights, or would equal 1. Okay. The other way you can do it is you get a density. Okay. Do you guys know how the height of a density histogram is determined? Okay. So notice this bar has a density height of 0.1. Okay. So the way densities work, okay, density histogram okay, the density is going to equal the relative frequency divided by width of the bar. Okay, so for values between -2 and -1.5, our relative frequency is equal to 3/60, equal to 0.05, and then my density would be equal to 0.05 divided by the width of the bar, which is 0.05 divided by the width of the bar is 1/2, right? Density equals relative frequency divided by bar width, which is, in our case, each bar has a width of 1/2. So my density here is going to have a height of 0.1. And the thing about the density is that the area of each bar is going to be equal to the width times the density, which is equal to the relative frequency. And so the sum of the areas is going to equal 1. Does that make sense? For the density, if the height is the relative frequency divided by the width, then the area of the bar is going to be basically the relative frequency. And so the sum of all of the areas will equal 1. Okay? And so that's how density histograms work, is that the sum of all of the areas, if you calculate, okay, what is the area of this bar, all right? The sum of all of the areas add up to 1. Much like, I guess, a probability density graph. So anyway, this is basically your frequency histogram, and you got I guess, your density histogram. And a kernel density estimate is kind of like, can we draw a smooth curve that fits this histogram? Can we draw a smooth curve that fits this histogram? And if I try to draw a smooth curve that fits the histogram, maybe it looks something like this. Okay, so we kind of want to get a smooth histogram. And you might say, well, what if I want to make it smoother? Okay, you can do that, and it looks kind of like this. Okay, what if I don't need it to be as smooth? You can do something and you get something like this, right? And so here on this one that is much less smooth, you have like a peak at, you can see the rug plot of the individual dots. And so you get like this tiny little peak here, a tiny little peak there, tiny little, there's like 3 values very close to each other. And so you get kind of a peak right there, and so on and so forth. And this feels like it might be a poor fit for the histogram, and so you could try adjusting the histogram to have more breaks or more bin widths in it, and you get something that looks like this, and you can see, oh, okay, this kind of aligns between, there's better alignment between like the peaks and all of the heights of each of these bars and stuff like that. Okay, so the thinner bandwidth results in kind of more jagged peaks, and this is similar to having a histogram with really small bin widths. This is probably not the best way to illustrate the data. I would think if your histogram has this many breaks, it's not a great one. But anyway, this is what you end up getting. Okay, but I want to talk about how this thing actually works. And so here is a very silly data set for which you would never in real life actually create a kernel density estimate, because here we only have 3 data points. But I think it does illustrate how the kernel density estimate function works by being able to see just the 3 individual points. So I have 3 values, -1, 0, 2. And I'm going to intentionally plot a very narrow bandwidth of 0.1. Okay, so the default density curve is kind of like a Gaussian curve with a standard deviation of your bandwidth. So standard deviation 0.1 on Gaussian says what? 95% are within 2 standard deviations, 99.7 are within 3 standard deviations. And so you have almost the entire width of the normal density curve between, say, 2 plus or minus 0.3 here. So basically I have a normal density going from 1.7 to 2.3. Here I have one centered at 0, going from -0.3 to +0.3. I have one centered at -1 going from -1.3 to -0.7. And so you could imagine just dropping these little normal curves centered at each of your data points. One at -1, one at 0, and one at 2. Okay. What I'm going to do is I'm going to increase the bandwidth on our next plot. So here I'm going to increase my bandwidth to 0.25. And just imagine this animation of kind of like this normal curve dropping down. And then another normal curve dropping down, but where there's overlap, they like stack on top of each other, okay? So here, you know, if I have a normal curve dropping down and a normal curve dropping down, and they're far apart away, they look like just separate normal curves. But here, these two normal curves are falling down, and then they end up kind of stacking on top of each other. And so where there's overlap, we get kind of this smoothed out valley in the middle, okay? And so this one is normal curves with a bandwidth of 0.25. So, you know, you go out 2 standard deviations, and that's going to get 95%. 3 standard deviations will be, you know, 99.7%. So here I have one centered at 2, and it's probably going from like, you know, 1.125 to 2.75. And here the one centered at 0 and the one centered at -1, there's going to be a little bit of overlap between them, and so you get kind of this smoothed out thing. And as you increase the bandwidth, the normal curves start to kind of stack on top of each other and smooth one another out. So you get something that looks like this, okay? And as you increase the bandwidth, you know, things get more and more smooth. You know, at this point, it's kind of silly having such a wide bandwidth, especially because we have only 3 data points at -1, 0, and 2. But you can kind of see what's happening as you kind of increase the width of these normal curves. I hope that kind of illustrates what's going on, okay? And basically, the same kind of thing is happening here. It's just you have a whole bunch of data points, 60 of them, and you could just imagine each one gets its own little normal curve centered at each value, and then where they overlap, they kind of stack up higher and higher. All right, and so you can kind of see it with this dot and this dot and this dot, and these 3 kind of overlapping together. And as you kind of change the bandwidth, you know, overall, this is kind of the smoothed out shape that gets formed when you do a kernel density estimate. All right, and so that's kind of how it works. There are other shapes that you can stack on top of each other. I would say the Gaussian is probably the favorite of these things that get used, but just to kind of illustrate, you have the Epanechnikov. I think that's how you pronounce it. I don't know. It's basically an upside down parabola. You also have the rectangular, which are basically rectangles, but because the way they get plotted, they look a little bit more trapezoidal, but underneath it, they should be rectangles. Okay, you have the triangles, you have cosine, and so this is what it looks like. So here's our upside down parabolas with narrow bandwidths, and again, we would never do this in real life with 3 data points, but just so you can kind of see what happens when they start overlapping, you get these funny little shapes here, okay? And so this is what happens when you stack parabolas on top of each other, okay? And again, it looks funny. In a larger data set, it looks better. But okay, here it is with rectangles. When you start adding rectangles on top of each other, okay, so here the bandwidth is wider, but not quite enough to make for overlap. And then when they start overlapping, then they just look like you're stacking blocks, okay? And this is what you end up getting. Here is triangles, and then when triangles stack, like when these 2 overlap, you end up getting these flat regions between the 2, okay? And so that's what happens with triangles, okay? And then with cosine curves, they behave very similar to adding Gaussians. It's just slightly different properties. And again, with all of these things, the goal of all of these things is to just kind of get some sense of, can I estimate what the underlying density curve looks like, okay? Again, this is just a numeric approximation method. So contrary to what you might think, when you look at this, you don't have an analytic form for this thing. Like if you say, hey, what's the function that produces this curve? We don't have an answer, right? Like when you have a PDF, of the normal distribution, you have like some kind of answer there. Okay, here we don't actually have the answer. I mean, I suppose it's just it's the sum of a whole bunch of individual kind of like PDFs added on top of each other. But really, it's just the output of this computer program, and it just says, hey, let's kind of add up all of these numbers and stack them on top of each other, and we get some kind of shape. And it just says, at this point, my density estimate is 0.05, and my density estimate at this point is 0.15, and my density estimate is at 0.25. And so you just kind of get a sequence of what your density estimate is, but not like a analytic form where you say, I'm going to plug in X and I need to get out a Y. Okay. The default bandwidth for its calculations is determined by this kind of formula. But again, you can kind of specify the bandwidth yourself, and here I've been kind of fiddling around with different bandwidth numbers, 0.1, 0.25, 0.5, 0.8, and you get very different looking curves there. Okay, one thing that happens when you do kernel density estimations is because it's just kind of dropping these curves and stacking them on top of each other, sometimes you get these weird, not weird things, but just the natural thing that happens is you end up getting tails that extend outside the region where you've collected data, which in a lot of cases is fine, but in some cases it doesn't make sense. So for example, if you're dealing with a Poisson distribution or an exponential distribution, which produce only strictly positive values, okay, because of the way this tail works, the tail might go into the negative territory, and obviously that's not going to be the case. So just be aware of that. It's just a tool that we can use to estimate things, just to get a sense of the underlying data without necessarily using it to say this is what the underlying thing looks like. Okay, we'll wrap it up here. Let me give you your last view quiz answer. The letter B as in bear, is our final view quiz answer. And so yeah, on Wednesday I'll just talk about what you can expect on the final exam, and then we'll take Friday off. So have a great rest of your day. Hope your 10th week goes well. Good luck on your finals and whatnot, and we'll see you Wednesday.